Hello, I've been working on an asynchronous job system that uses NAS JStream for storage. It's super early days. I'm still working on bugs and finding the direction I wish to go exactly. But I'll do a quick demo of what it is and how it, where it is today and what I'm trying to build. So I mentioned it's a JStream based storage system. So at the top window here we have a working JStream server. And if I do AJC info, we'll see I have task storage, which is a stream where the definitions of a job go, and I have a default work queue. The work queue contains entries that says, just complete this task, and it points into the task store. So you could have multiple work queues, you could have different concurrency, you can have different runtimes, you can have different maximum lifetimes, you can different retries, all this kind of stuff. And even while it's set up here, the default one, you can adjust through command line editing many of the settings on the fly. So we have task store. Let's add some tasks. We'll add 20 of them. So I'm adding a task. It's going to go into the default work queue by default. I'm giving it a routing key, email.new. We'll see a little bit of how that works later on, but every message gets a routing key, and then the system will pick a handler for handling the appropriate message. So if you, for instance, had a handler for email.new exactly, it will process. But you could also have a handler for just email, which will get all email-related tasks. This is just some stub JSON that we stick in there just to show something. So the tasks have been in queue. It's a little bit slow because it spawns a command every time and connects and so forth, but you see the task is there, it's been created, and of course underneath it's actually a piece of JSON. Now for demonstration purposes, I'm going to run these tasks through a shell script. And the shell script just fails randomly, like 10% of the time. It sleeps a little bit and then it produces output hello world. So it doesn't do anything, but it, I have to demonstrate the system. Now, we can say process the tasks we want to handle email new messages against the default queue. We will do 4 at a time. In other words, it will take 4 messages awaiting work queue items and spawn our temp process SH 4 times concurrently. We want to have Prometheus data on port 8081, and any failures should result in a back off based retry for up to 1 minute. It's taking messages, it's handling them as doing retries. The pauses are because of course it's sleeping between 0 and 10 seconds. So when it pauses, it means all processors are busy. I'm guessing it's finished now. Yeah, the queue is empty. We can start another one of these processors. We just have to give it another port. So now we've scaled to a second process that can also handle 4 concurrent emails, and so we have 8 concurrent. And if I again ask to add these emails, you can see they're both handling messages, so we've got 8 in flight. They're retrying, and retries will fail over and all this kind of stuff. And it's gone through. So that's the basics of the system. Now this is implemented in Go. You can write your own handlers. You don't have to run shell scripts. I'm just using shell scripts here for a demo. The real idea is that you write a handler in Go that looks a little bit like, where is it? It looks a little bit like this. You create a handler. It takes a context for how long you have to process a task. Sets you up a logger, it gives you the task. You reply with any data you want. Here it's going to be success and an error. An error will by default, any error will result in a retry based on the backup policy. And if you have if let's say this message is corrupt, it's invalid JSON, it's never going to work. No matter how many times you retry it, you can decide to terminate it by returning instead error task like that, which will just terminate the task immediately and not retry. Anyway, so that's a handler. That is literally the amount of work I want you to do to set up a thing to handle emails, and you just focus on your task at hand. Now, if you stick that handler into a Git repository, and I want to turn that into a container really quickly. Before we do that, let me show you one other aspect. Nats is a request reply system. In other words, you can do RPC. So what I'm doing here is I'm setting up a subscription on a particular subject. Any message that gets there, it's going to reply to the message with the word text. Now let's make it a little bit more interesting. Like that. So it connects, it's waiting for messages from that subject, and this scales horizontally. There's failover, regional failover, scale up, scale down, all kinds of stuff. It's really, really nice. There is a full service mesh actually built into the Nats broker for that. And what I really want to do is to be able to use that, because I had a shell script handling the messages here, but what if I wanted to use any of the other 40 languages that Nats support, and I want that to run as a service that's long running? You can start up a service written in Java, Node, and TypeScript, and any of these languages, run it like my CLI is there at the bottom, and delegate task execution to that. And the way that looks is like this. So I'm starting up just like before, but instead of giving my shell script, I'm telling it remote. And it will now figure out how to handle those tasks across the NAS network. And if I add some tasks, you'll see on the right hand side, it's handled all of our tasks. The request comes in, it has a content type that indicates this is a task from Choria Asynchronous Jobs in JSON format, and it gives you a deadline, which is how long the task has to complete, and the full task in a body, right? Now, if we look at the task that's been successfully processed, you can see it's completed. There's some payload there. Let's have a quick look. Result, payload, which is base 64. Okay. Remote true. So these are the responses from this remote piece of code. So you can implement handlers in any language that you wish. Deploy them against your next NAS rig, run them in Kubernetes, run them in however you like, bare metal machines, any way you wish to run these things, you can run them, and it can handle these messages. So you can implement them in any language, use any libraries, do whatever you want. Now, of course, I'm using a CLI here to drive the process, but you can't run the CLI all the time. So this is a way to test and interact with the system. What you really want is to basically have, let's say, a container that is specifically set up. Perhaps it compiles in a Go handler, perhaps it calls out the remote handlers, specific versions of those dependencies, Prometheus data, monitoring data, run it in Kubernetes pods, scale it out horizontally, using your autoscalers, all your policies, everything you want in Kubernetes. We want to support all of those deployment methods to run these handlers and to run the schedulers and so forth. And so to do that, you have an Asyncjobs file that describes how you're going to connect to the network, what queue you want to process, what you call the thing, which version of the Asyncjobs system you wish to use, and now you set up your handlers and your routing. So we're going to send email.new messages to this Go code and audit.log messages to a remote handler, like the one that I showed you earlier. And the code, of course, is this code. for the handler. So you just make that, stick it on a Git repository, and point it into the Asyncjobs file. You then go ajc package to Docker, and we'll support other methods in future. And what you'll see is it's output a Docker container for us, and we can just go build it. So this will take a little bit. We let that run. It will take a little bit. I will probably forward the video a bit, but this essentially creates an Alpine Linux-based container that has one binary in it, in addition to Alpine, and that's going to be a Go application that has compiled in this code, and it has pulled in support for our callout remote. It supports Prometheus, it supports debug logging, informational logging, supports custom context, custom concurrency for scale out and for scale up. Yeah, all the different custom work queues, everything. But the default is going to be what's in the file. Now let's have a look at running this thing. So I've made my context earlier, for the AJC context for connecting to this. So I'm mounting the context into the container. On the documentation, there's a way to show you how to mount just the one context into the container. Context is how NAT connects to the network. NAT has vast amount of options for connections. Even WebSockets, you can use different credentials, TLS or not, different ways to find the address stream. Massive amounts of options. I don't want to support all those options. So context, though, encapsulates all of the available options, and so we just use those. And you can see our handler is up. Looks familiar to what we had earlier. And if I add some new jobs, it's handling them. So that Docker container is running and is doing what we saw earlier. You can deploy this thing to your Kubernetes, etc. And as you can see, it's exposing the Prometheus metrics, so you can make dashboards, all that kind of stuff. So that's basically the system. In the follow-up video, I'll talk a little bit more about the code and do a similar demonstration of achieving some of these things in Go, no CLI interactions. It's fully supported. Everything I've shown you is possible in the APIs. And we're working towards what is next for this. I want to add things like job schedulers, job dependencies between them, and so forth. I'll say one little thing about the job store. We can see here there's 80 messages in my task store. Now obviously these things will fill up, and I'm keeping them forever, so not good. We do support a method where you can configure the system to say drop all completed messages. In other words, as it goes through the task handling, and let me show you something. There's a little life cycle for tasks, and you can see on the right hand side life cycle events telling you how these tasks are processed. They go from new into active into complete. Now what you can do is once it reaches complete state, you can tell the system just to discard it, throw away the task. And so in effect what's going to happen is what is left in the task store is essentially a dead letter queue. And then you can say, take this task and task retry and oh, there we go. And it will just retry that one task, and as you can see, the tries are going up every time that it's been handled. And so the idea is that the task store can be self-cleaning, so you can say drop all terminated messages and all completed messages, keeping only the ones that's unprocessed or been there for a long time or has reached a specific max tries or a specific deadline, because every message has a deadline. And then those messages can stay there, and you can deal with those messages that are in that fail states by either purging them, or retrying them, or deleting them individually, or whatever you like to do. It gives you the control over all of those kind of systems. So there's an inherent task store based data queue, which is quite an interesting approach to handling that for work queue based data queues, which is quite a complex thing to do. So that's the system. That's roughly what I'm working on. It's early days. We're still figuring out exactly what works well for JetStream, what cannot be done on JetStream, getting all the mechanics of this kind of things right, because it's quite a lot of moving parts. And we move on to scheduled tasks where you will be able to store in JetStream essentially cron jobs, and on that schedule it will create tasks for you on demand. So you can say every morning at 5 a.m. create a email maintenance task that you do to clean up spools, for instance, or something like that, or email report that sends off a report about the day's emails, or anything like that. And why not just stick it in cron? Because these things they will fail over, they will scale up, they will scale down. So in a cron you would have to put it into etc cron tab on the server, and what if the server dies? Or you have to have two machines running the cron tab, and now you get duplicate entries. Then you have to have complex locking. It's craziness. This system allows you to basically solve that. You put the task in the system, and any available handler handles that task once only, or multiple times if it requires retries if it's failed. But it's a distributed cron system, so I'm going to work on the scheduler. And there's a number of other things I need. The problem I have myself to solve is this cron system, and so that's towards where I'm working with this. Anyway, it's early days. Details are on the screen, and please join us in the community. Give me feedback. Give me your ideas. I'd love to hear them, and together we can build something really cool for the NATS community. Thank you very much.